Hello everyone, this is Dr. Webb. In this video, we're going to be looking at one of the most important applications of calculus in general, but specifically for multivariable functions, and that's doing approximations. So let's start with an actual sort of applied problem. So we have a company, and it estimates that for every $1 increase in its labor expenditures, the value of production increases by $1.20. And for every $1 increase in capital expenditures, the value of production increases by $1.15. If the company increases its labor expenditures by $5 million and decreases its capital expenditures by $4 million, estimate what the total change in the value of production is. Okay, so going back and looking at this, we see that its labor expenditures are increasing by $5 million. And every dollar increase in labor expenditure causes an increase in production by $1.20. And so from labor, well, we'd have the 5 million times $5 million times $1.20. So let's write it as 5 million. So that's the change in labor times, well, every dollar increase in labor causes a $1.20 increase in production. And so multiplying these two together, 1.2 times 5 gives me 6. And so we'd have $6 million change in production coming from the labor. And then for the capital, well, it's decreasing by $4 million. And so it's decreasing by $4 million. And we're given that every $1 change in capital causes a $1.15 change in production. So we multiply this by 1.15. And what is 4 times 1.15? Pulling out my calculator. That gives me minus 4.6 times 10 to the 6th. And so putting these two together, adding these two together, we get 1.4 times 10 to the 6th. And so what we're saying is that we're expecting a $1.4 million increase in production. Okay, and this is a pretty simple, straightforward problem. But now let's try and look at this sort of in the context of what we've been talking about, in terms of partial derivatives and multivariable functions, right? So at the beginning, we have the $1 increase in labor expenditures. For every dollar increase in labor expenditures, the value of production increases by $1.20. So this is change in production per change in labor. And so this $1.20 we can think of as being change in production over change in labor. Or really, it's kind of talking about a partial derivative of production per labor. The $1.15, well, that's talking about change in production over change in capital, and so usually K is used for capital. But really that's sort of thinking about that as a partial derivative of production in terms of capital, right? And so the $5 million increase, that's talking about a change in labor. And the $4 million decrease in capital, that's talking about a change in capital. And so really, overall, what we did in this problem is, clearing out some space, is when we did $1.20 times 5 million, really we were thinking about this as sort of taking the partial derivative of production per labor and multiplying it by the change in labor, and then doing the decrease of $4 million times $1.15. That's talking about the $1.15 is the change in production per change in capital times change in capital. And then when we added those together, we were estimating, actually it was an estimate, so let's write it as an estimate. We would be getting approximately the change in production, right? And so values going in here, the partial derivative of production per labor, that's $1.20. Change in L, that was 5 million. Change in production per, the partial derivative production per capital was $1.15. And the change in capital, that was minus 4 times 10 to the 6th. And so then when we added these all together, we got delta P to be about 1.4 times 10 to the 6th. Okay. So let's look at this, this example right here. It looks a lot shorter, but it is, in fact, has pretty much all the same information. In fact, it has a little bit more information. And so we're given a function of two variables, and we're told that the value of the function at the point 4,3 is 12. The value of the partial derivative in terms of x at 4,3 is minus 2. And the value of the partial derivative in terms of y at 4,3 is equal to 5. Okay, so the first question is, it wants us to estimate what's the value of the function at 4.3 comma 3, right? So what's the change between 4.3 comma 3 and 4.3? Well, we have that x has changed by 0.3, but y stayed the same. So delta y is 0, right? And so we have this change in x by 0.3. How do we, what's going to tell us how we expect that to change the value of the function? Well, the partial derivative in terms of x tells us about the change in the function per the change in x, right? And so we'd expect the change in f in total to be the value of this partial times the change in x, actually approximately. And so this is really coming from the idea that change in f over change in x is going to be what the partial derivative is telling us. And so then plugging in values, this is minus 2. Change in x is 0.3. Multiplying together, we're going to get minus 0.6. And so we're expecting f to decrease by minus 0.6. So f started at 12. And so we'd expect f at 0.3 comma 3 to be approximately 12 minus 0.6, which is 11.4. Okay. So what if instead we wanted to estimate the value at 4 comma 3.2? Well, so here the difference between 4.3 and 4.3.2 really is x hasn't changed at all, but y has increased by 0.2. And what's telling us what that change in y should do to the value of the function? Well, that's the partial derivative in terms of f. Right? And so, same as before, we'd expect the change in f to be, take the partial at 4, 3, multiply by the change in y. And so the partial at 4, 3 is 5 times 0.2. And so that's giving us 1. And so then that tells us that we'd expect f of 4.32, 4 comma 3.2, to be about 12 plus 1, which is 13. Okay, exact same idea as the previous one, except this time we're using y. Okay. Now, what if we change both x and y? Right, so we're kind of combining the two together. And so our change in x now is from 4 to 4.3 is 0.3. Our change in y is 0.2. And so we'd expect our change of f, really this is putting the two together, to be the change in x times the partial in terms of x. That's going to give us the effect of x. And then we're going to add on the partial of the partial in terms of y times delta y. That's what the change in y, that's how the change of y is affecting it. And so putting these together, we already did all the work for this. 5 times 0.2. And so this is 1 minus 0.6. Which will give me 0.4. And so we'd expect f at 4.3, comma 3.2 to be approximately 12 plus 0.4, which is 12.4. Okay. And so this is how we'd expect, if we know the partial derivatives, this is kind of gives us a way to think about what's happening to the function around that point, 4 comma 3. Okay, and so just kind of putting together what we did in these two examples, if we have z is equal to f of xy, so we're thinking about this as a surface, and then around the point AB in the domain on the xy plane, well, we'd expect the change in z when we change x by delta x and the change y by delta y to be, you take the change in x and multiply it by the partial in terms of x. You take the change in y and multiply it by the partial in terms of y, and then we add those together, right? And so this term, this first term, f of x, the partial in terms of x times delta x, this is talking about the change in x's effect on z, and then let's change colors. The second term, the y term, this is talking about the change in y's effect on z. Right? So to get the total effect on z, the total change in z, we just add those together. Okay, now if we replace delta z, well, what is delta z? Really, it's the difference between our new z value and the original one, which is f of ab. Delta x, well, that's really to figure out delta x, we're figuring out how far x has changed from a. So delta x is always x minus a. And the change in y, well, we get the change in y by, taking our new y and subtracting off the original y, which is b. Okay? And so this approximation that we're playing with, we can rewrite it in this form. And then if you notice, if we want to get our new z value by itself, well, we can move this f of ab over to the other side. And so if we're solving for z, well, we get a new function. And actually, this shouldn't say ab, this should say x, y. We get a new function that's in terms of the variables x and y. The a's and b's and the values of the partial derivatives are all constants. So this is what z has become. This is our approximation. And so this is what's called the linear approximation of f of xy at ab. So what makes this linear? It's that x and y are both to the first power. They only appear by themselves to the first power. And so that's what makes this a linear approximation. Okay. So if you look at this, this again should be x comma y. Sorry for the typo. If you look at this, this is a linear approximation that we have for two variables. This is really similar to the linear approximations that we saw in Calc 1. So remember this linear approximation in Calc 1, this was the tangent line. And in Calc 1, if you have y is equal to f of x, how do you get the tangent line at x equals a? Well, the slope is going to be the value of the derivative at a. And then using then the point slope formula for a line, it's going to be the slope times x minus a. And so this again is representing delta x plus the original function value. Okay. So what do we have here? Well, what has happened to that slope? Well, because we're in two variables, now we have to look at the effect of both x and y separately. And so the slope times x minus a, it's kind of split into two. One part to represent the change in moving in terms of x, and the other part to represent the change in terms of y. Now, if we were to hold either x or y to be constant at, if we hold x, say y to be constant at b the entire time, well then this term would disappear and we'd end up with the same type of line that we had before. Right? And so that's sort of coming from the fact, this is tying into the fact that this calculation of the partial derivative really is calculating the slope of the tangent line when we slice it along the plane y equals b. And so that's how we can see that in this equation. Similarly, if we were to fix x to be equal to a, well then we'd have a minus a, and this term would disappear, would zero out. And so what would be left with is what looks like the equation for a tangent line. And in fact, that's the equation for the tangent line. Well, this takes the intersection of the surface and the plane x equals a. And so this will be the tangent line along that plane. And so in some sense, this linear approximation really is coming from combining these two lines. Okay. So let's go back to, let's write this back and think about this as a graph. Z is equal to this linear approximation. Well, what if we moved Z now to the other side? So we can rewrite it as 0 is equal to the partial in terms of x times x minus a, plus the partial in terms of y times y minus b. And then I'm going to write minus, and so that I'm matching z minus f of ab to y minus b and x minus a. And this is the equation we get. Well, so looking at this, remember, this is a constant. That's a constant. And then out here, we have a constant. You can think about this as constant being minus 1 on the outside. And so we have a constant times x minus a, plus a constant times y minus b, plus a constant times z minus f of ab. Well, what does that look like? That's the equation for a plane. Right? So this would give us an equation for a plane through the point. Well, the point, remember, we look at what each of the each of the variables is being subtracted by. And so x is being subtracted by a, y is being subtracted by b, and z is being subtracted by the value of the function, f of ab. Okay, and so that's a point that the plane goes through. And then to get the components of the normal vector, and I should have used vector brackets here. So let's draw those in. Well, the components of the normal vector are coming from the component for x is the x coefficient, which is the partial derivative in terms of x. The component of y is the y component. And then the component of z is going to be minus 1 because we're just subtracting off that term. Okay, and so this naturally gives us the equation for a plane. And so because this is a plane and it is the approximation for the surface, at that point we're going to call it the tangent plane to the surface at the point AB. Okay, so let's do an example on how to figure this out. Right, so we want to find the tangent plane at the point 2 minus 3. Okay, so what are the things that we need to figure out? Well, you got to remember that our normal vector for this plane is going to be the partial in terms of x at 2 minus 3, the partial in terms of y at 2 minus 3, and then the z component is always minus 1. Okay, so we got to figure out these two partials. So fx is going to be 3x squared plus derivative of 4xy squared in terms of x is going to become y squared. And then the minus y at the end is just going to go to 0. And so if I plug in 2 minus 3 into that, I get 2 squared is 4 times 3 is 12, plus 4 times 9 is 36. 12 plus 36 is 48, I believe. Okay, the partial in terms of y is x cubed goes to 0. I'm going to get from 4xy squared, well, 4x is like a constant, and then derivative of y squared is going to be 2y. And so I'm going to end up with 8x times y. And then minus y at the end is going to give me a minus 1. And so when I plug in 2 minus 3 into this, I'm going to get 8 times 2 is 16 times minus 3. 16 times minus 3 is minus 48. Minus 1 again is going to give me minus 49. Let's see, double check that with my calculator. So 8 times 2 times minus 3 minus 1, yes, gives me minus 49. Okay, and so now we have our normal vector. N is 48 minus 49 minus 1. Okay, and then we have the x and y coordinates of our point. We need the z coordinate for our point, which is going to be plugging it into the function, plugging 2 comma minus 3 into the function, which is going to be 8 plus 4 times 2 is 8 times 9 is 72. Minus 3 is going to give me plus 3, and so I think that is 83. Yeah, 8 plus 8 times 9 gives me 80. Add another 3 gives me 83. And so we have our plane is going to be 48 times x minus 2. 2 is coming from our x coordinate, minus 49, which is coming from our partial in terms of y, times y plus 3. And plus 3 is coming from the fact that the y coordinate we're starting at is minus 3. And then, last but not least, minus, the minus 1 is always minus 1, times z minus 83. And 83 is coming from the value of the function. So there's our point normal equation for the plane. And we can leave it just like that. Okay. So in general, we say that a multivariable function is going to be differentiable at a point AB on the xy plane if the two partial derivatives at that point are both continuous. Okay. So if both of the partial derivatives are continuous at that point, what that means basically is that we can make the tangent plane, and that means that, so having that the partial derivatives exist there allow us to make the tangent plane. Having them be continuous at the point means that this is going to be a quote-unquote good approximation for the function around there. That this plane is actually going to match closely to the shape of the surface there. Okay, so for an last example for this video, we're going to take a function, and the question is find the points on this plane where the tangent plane is going to be horizontal. So we want to find all the values of x and y where the tangent plane to this function is horizontal. Okay, well, so since we want the tangent plane, we need to figure out the normal of the tangent plane. And so just recall the normal of the tangent plane is going to be partial in terms of x, partial in terms of y, minus 1 for the z. So we need to figure out the two partials here. So partial in terms of x is going to be 2x minus 2y. The plus 3y squared has no x in it, so that goes to 0. And then we have a plus 4. The partial in terms of y is the x squared has no y in it, so that goes to 0. We're going to have minus 2x plus derivative of 3y squared is going to be 6y. And then we have plus 4x. That's going to go to 0. So those are our two partials. Okay, so we have our partials now. Now we got to figure out what does it mean for the plane to be horizontal. Well, if the plane is horizontal, that means it's parallel to the xy plane. And so what would a normal vector for that be? That means that the normal vector for this is going to look like, have no x and y components and only a z component. So something in here for z. It doesn't really matter what. Okay. And so that means that in particular, since our normal the normal that we're getting from the function is always having this -1 in the z component, we can actually, since we can have anything we want in that z component, there's lots of different normal vectors to a curve, to a plane. We can plug in -1 there. And so what does this mean that we want this normal vector to be? Well, we want both the x component to be equal to 0 and the y component to be equal to 0. If both of them are equal to 0, then our normal vector is going to look like that, which is going to mean the tangent plane is horizontal. Okay, so we got to figure out the x and y that make both of these equal to 0. Okay, so maybe let's start off with minus 2x plus 6y. So I can rewrite that as 6y is equal to 2x, which gives me that 3y is equal to x. What can we do with this? Well, I can now take that and replace that in for x in the other equation. And so in this equation here, we get 2 times 3y minus 2y plus 4 equals 0. And so this is going to be 6y minus 2y is 4y. Move the plus 4 to the other side is equal to minus 4. And so then that means that y is equal to minus 1. And then plugging that back in to there, we get that x is going to be equal to minus 3. Okay, so there is one point on the xy plane where the tangent plane is horizontal, and that is precisely at minus 3, minus 1. And that's our answer. Okay, and so in the same way that having a horizontal tangent line became important for certain questions in Calc 1, knowing where a tangent plane is horizontal is going to be important for certain questions in multivariable calculus. So we will definitely be seeing questions like this again. That is all for this video. I will see you again soon.